Thank you, Drew. Thank you for this nice introduction. Thank you also for the invitation. It's really a pleasure to be here. We're starting again to have talks in person. I think it makes all the difference. So, as Drew said, I'm here visiting from NYU, and my visit here has been made possible by the Center for Data Science. So I'm very grateful to them. And I think behind them there is CFM, which contributed to the funding, and I think is sponsoring this lecture as well. So I'm very grateful to them as well. I think they're following the talk online. So what I'm going to be discussing today is some interplay between machine learning and applied mathematics, what one can do for the other, and vice versa. And it's joint work that was started with Grant Rotzkopf when he came to work with me as a postdoc at the Crown Institute. He's now faculty in Stanford in the chemistry department. And the work will also involve my colleague Joan Bruna, Marine Gabriel, who was a postdoc at CBS but is now coming back to Paris. She will be faculty at the Polytechnique. And Zheng Dao Chen, who is a student at NYU. Okay. So, as Julio mentioned, I'm an applied mathematician, and so I am in part interested in doing scientific computing. When you do scientific computing, typically what you need to do is manipulate functions on a computer, and when you do that, one way or another, you need to discretize them. And when you discretize function on a computer, there is something that hits you, and that's called the curse of dimensionality. That's a term that was coined by Bellman in '61. And essentially, the curse of dimensionality says that gridding space becomes harder and harder as the dimension of space increases. And as a result, the number of operations that you need to do, if you want to compute to a certain precision, depends exponentially on the dimension. That's the curse of dimensionality. In essence, it's saying that functions in high dimension are typically quite complicated, at least in the worst case scenario. Now, so this was a fact of life. It is a fact of life, and something that was, precluding even thinking about doing certain computation. Like, for example, if you were to want to solve partial differential equation on a computer, we would not think about doing that if the equation was in 10, 20, or 100 dimensions, simply because the common wisdom was to say it's just not possible to do that. The curse of dimensionality will, kill you. But then we have seen all of these amazing new development from machine learning. I'm just, showing you two of them here that epitomize, all the others in a way. That, in fact, have shown us that at least in certain cases, it looks like learning in high dimension is possible. But there is something out there that we didn't know or we didn't suppose was possible, but indeed it is. Because, for example, if you take the game of Go, viewed as an input-output problem, right? You need to figure out, the machine needs to figure out where to put the next stone on the board. There is zillions of possibilities for that needs to be taken into account. Okay, and so the theme of the talk will be essentially to try to understand whether we can somehow make sense of this reckoning in a way that we were living in a world where doing things in high dimension was not possible, and well, certainly it looks like it is. Okay, and the two themes that I will elaborate upon is when, how, and why can neural network approximate high dimensional functions? That's one thing. And then, can we, if that's the case, can we then exploit these neural networks to revisit certain scientific computing problems that were thought intractable before because of the curse of dimensionality? Okay. Now, the picture that I'm going to give you here is, of course, very preliminary, and it's part of a big puzzle where people from all areas are contributing. I'm just going to give you one viewpoint that is certainly not the end answer, but might be a part that will at the end be a piece in the solution of the puzzle. Okay. Now there is another reason why we want to understand this, which is besides the fact that this is we would like to understand why it's working, but there's also a need to do that if we want to push forward the usage of machine learning. Because what is happening right now is that when you look at deep learning, it's actually extremely costly in terms
not only of data that is needed, but computing power that is needed. And this is illustrated on these two graphs. I apologize, resolution is maybe not very good. The one on the right is showing you what is, the number of operations essentially that are needed to train neural network. And this is the linear scale here, and log in the y-axis. So this is like Moore's law. Actually, it's growing faster than Moore's law because it's 3.4. Okay, it goes from the beginning like AlexNet, right? It's not really the beginning. It's the beginning of the monet age in machine learning, all the way to alpha go 0 and alpha 0, which are at the top. Okay, and there has been like a 6-10-fold, many decades increase in the computing power that was needed. Now, the left graph at the same time show that the scales are opposite. It's no linear on this axis, and the x-axis is logarithmic. And it shows you what is essentially how performance increases with the amount of data. And you see that going from 10 million samples in ImageNet to 300 million in ImageNet plus 300M, in fact, leads to an increase that at most is logarithmic, but essentially is not very, the slope is actually fairly small, okay? And so if we don't understand better what's going on with these, with these curves, well, many of the calculations that are being done there will be a little bit like Apollo moments that can be done, by Google, but certainly that you will not be able to reproduce on your laptop or even on computers at universities, for example. And so that's, there's a need for theory to see whether it's really necessary to go, to be so hungry for data and computing power, or if we can actually do better than that. Okay. So now with these preliminaries, like if we now want to go back and try to understand what's going on with machine learning and deep learning, right? It's first important to try to contrast what's being done in machine learning with what is done if you do standard function approximation, okay? And that's what I call feature and puzzles of nonlinear learning. And there are essentially three of them that make things, when we train neural networks, very different than what happens with the standard approximation. The first is that a neural network approximation is a nonlinear function representation. That means that unlike Galerkin truncation that are typically used, where you use a fixed truncated basis with linear weights that you need to adapt, in neural network, the parameters enter the network in a nonlinear fashion. And in fact, it is believed that it is very important, this structure, this convolutional and compositional structure of the neural networks, is thought to be very important for their expressivity. But at the same time, they make the problem much more complicated into trying to understand what is the power of approximation of these networks. So that's the first question. The second question that makes things quite different is that when you train a neural network, you're doing that typically by using data in high dimension, and that means that the data is very sparse. So unlike what you do when you do standard calculation on a grid, where you look at every point on the grid, what the function is doing, you can't do that here. There is no grid to begin with, right? And typically the information that you have is very, very sparse. Think again about, the game of Go, which is the machine has played an enormous amount of part with itself, but that is still a very infime portion of all the parts that are possible. And yet you want to train the network on this training set that is very small, and hope that it will perform well outside, so that it will generalize outside of this training set. So that's the generalization error. And in order to understand that, we need to understand what is in the data structure that makes learning possible. Second. And then the third aspect is in fact related to the first, is that, well, when you train a neural network, you are optimizing the parameters. But since the parameters enter non-linearly, this is non-convex optimization. So a priori, you need to expect that the lost landscape that you are using to train the parameter will be highly non-convex with many, many local minima. And so there's no reason a priori why, if you use gradient descent or stochastic gradient descent, it will converge to a local minima that is any good. It could get stuck somewhere. And that's not what's observed in practice, so that's yet another puzzle that you would like to understand. Okay? So as I said, I would like to look into this problem by presenting now what we have done, and as I said, is one way to look at the problem, which will be that will be complementary to many others, and this is something that is looking at neural network as interacting particle systems. So this slide is actually trying to explain that, and again taking the viewpoint that I'm really looking or viewing the neural network as a way to approximate function. Okay, and so you can phrase it in the following way, right? So what is a neural network? What is a nonlinear is a weighted superposition of nonlinear units. Think ReLU, like the first one, where C there would be the external weight, the phi hat would be the ReLU unit, and I'm going to use a compact notation, lumping all together using as parameter just theta, right? So you have this superposition thing, and this depends on the input variable x, and then on the parameters theta I. And what you need to do, there's m of them if you have a network with m. For the moment, let's just focus on shallow neural networks, so 2-layer, one hidden layer. We'll look into deep network later. And so what you need to do here is to train these m parameters, and the way you do that is essentially by introducing a loss function which measures the discrepancy between this approximation and a target function, f. Okay, you could use a square loss or inch, whatever, right? And that you evaluate on a test, on a data distribution that's given to you, which I will denote by nu x. Okay? Now, when you look at, you see that in this representation, I have weighted the sum by 1 over m. There's a reason for that. Namely that it is interesting to think about this representation as a discretization of an integral, which is in fact as a discretization of an expectation with respect to a measure mu of the unit. So in other words, it's interesting and useful to look at the neural network representation as being simply a discretization of a representation in which the function representation would simply be the expectation of the nonlinearity with respect to some measure in the parameter. Okay? This is what's behind this universal approximation term that I will describe to you in a minute. The reason why it's useful to do that is that there is two things that you immediately obtain if you think a little bit of this probabilistically, which is that first the law of large number guarantees that Fm will converge to F. So the discretization above will converge to the one that is below if you draw the parameter theta I with respect to mu and you take the width sufficiently large. And second, there is a central limit theorem that tells you that the error can be quantified because the central limit theorem tells you that the discrepancy between Fm and F scaled by square root of m is a Gaussian field. And that gives you, the statement, is the one that they've written here, which is to say that if you look at the expectation of the difference between Fm and F square, where you take the expectation with respect to the data distribution d nu, you can make the calculation exactly with the CLT. It actually gives you that this expectation is given by the right-hand side there. Okay? This, if you wish, is a measure of the error that you make if you use a network at finite width to represent the function f, which is given by this expectation. What's interesting is that you can use this to define a function space. In other words, you can use simply the estimate from the central limit theorem, right, to introduce a norm on the function, which is simply, well, you take this estimate and then you minimize it over all possible measures that preserve the target function, and you say that's the norm of this target function. And this is all fairly well known, right? If you do that, this norm controls both the approximation and generalization error. There's a two papers by Francis Back in Journal of Machine Learning Research that explains that, right? Which is that essentially, if you can control this norm, so functions that have a small norm of this type will be easy to learn. I'll get back to that in a minute. Okay. Now, these results, right, were part of this universal approximation theorem, and I'll go back to them in a minute. There were several reasons for which they were considered a little bit academic. One of them, or unsatisfactory even, is that this is a very static picture, so it's not very practical. It tells you that if you have a function which is of the type that it is, the unit that you have taken the expression with respect to a measure, and you knew this measure, you could represent it. In practice, however, you don't know any of this. And so the only way you can actually proceed in practice is to say, well, if I have a target function that I can evaluate pointwise on a data set, then maybe I will be able to train it in such a way that the parameters, so at the discretized level, will converge in a way that will control the error. So you need to put back the dynamics in this picture, which is the one of training. Okay? But that's something that I will explain now, right? So the question is, can we effectively learn in this space, the one that is defined, this norm space that's there, can we effectively do that, right? And this is where there has been, some development in recent years, and that's the one I'm going to, explain in the next couple of slides. And in a nutshell, and I'll elaborate on that on the next slide, is it's useful to look at the parameters in the network as a set of interacting particles and use the tools of interacting particle system to make certain conclusion. That's what's written in this box, in particular hydrodynamic limit and this central limit theorem. So let me try to explain that in some more detail, because that's, I'm going to just spend a little bit of time on that because I think that's useful. So suppose that you have a quadratic loss, which is measure the discrepancy between the target f and the neural representation fm, first line. So you can think about this loss as being a function of the parameters that are in the network. So it's a loss of theta 1 up to theta m if you have m sets of parameters corresponding to, these are the vector parameters that are in each of the units. Okay? So if you expand that, you can express the loss in the following way, right? And where there is the sum over, and there's a one body term, we will see this f, and then there's a two body term, which is the k, in the loss that they've written there. And then how would you do training in practice? Well, you take initial condition for your theta, for the parameters, and then you do gradient descent. Okay? Here I have written for you, because it's easier to think about, the continuous time version of gradient descent, which is just steepest descent, where the parameters are just evolving by going down on the gradient of the potential. Right? And I have written that in the population loss setting, but you can do that for empirical risk minimization, so if you use the empirical risk instead. I'll get to that in a minute. Now, as you see, what is interesting here is that you can view the equation of training as an equation for a set of interacting particles. And then you realize that because the parameters are indistinguishable in the representation, in fact, you don't care about what they do individually. The only thing that you care about is what the empirical measure does. Because if you know how these objects evolve, you can represent the function, because that's the same representation in the two gray boxes that are on the slide. Okay? And so instead of, if you want to understand theoretically what's going on, instead of focusing on the evolution of the parameter themselves, you can try to focus on the evolution of their empirical measure. And what is interesting is that, well, you can write down in this setup, because there is no noise actually, you can write down a closed equation for the evolution of this measure. I have written it, it should be written in weak form, I wrote it in strong form. This is just the Liouville of the Vlasov equation. So this equation here, for the parameter, induce this equation, it is an exact result for the empirical measure. Okay? And now I can try to make statement about what's going on at this level, which turn out to be much simpler than looking at what's going on at this level, right? Using statistical mechanics. In particular, I can take hydrodynamic limits. So I'm going to try to describe with a visual example what the hydrodynamic limit is, if you don't know what it is. I'm sure most of you do. So, the example here, you should think about the dots as being the nonlinear units in one neural network. Okay? And to make the visualization, I have just assumed that in the example there, these particles evolve in a double well potential. That's the one you see, and it's meant to represent this part of the loss. And then there's another part which is that you can't see, but that there's a repelling potential between the particles, which means that they want to go away from one another, and that's meant to represent, here I use the wrist-like potential, but that's meant to be a cartoon for what's happening here. I'm not going to use any of that later on. It's just to visualize things, okay? And so what happens if you look at gradient descent here, right? There is a competition, which is that the particle wants to be as low as possible on this potential that they see individually, but at the same time they want to be away from one another reasonably, because there is an energy cost if they are too close, okay? And the only point of the movie is to show you that instead of, you see, I have drawn particle randomly in one of the well, and now I'm going to make them evolve, and the only point of the movie is to show that the particles are doing things that are quite complicated individually if you want to track one of them. But if you want to track what their distribution does, which is essentially what your eye is actually showing you, you see that the evolution is much more simple. And so the evolution of this fluid of particle there is what is captured by hydrodynamic limit. Okay? And of course, that's an old story in physics, or to do this hydrodynamic limit, which we have revisited in the context of neural network. And so I'm going to summarize a little bit, in 2 slides what are the results that you can get from there. The first one is so there will be 2, there will be hydrodynamic limit or mean field, which is the equivalent of law of large number, and then there will be a central limit term. The law of large number, or the mean field, is essentially telling you this. It says, if you take a neural network with a finite width, and you train the parameter by gradient descent from well-prepared initial condition, that just means that you draw the initial condition randomly from some distribution initially, independently. Then there is a limit. The function that you represent this way has a limit when you take the width to infinity. This function evolves, and as it evolves, it will reach the target distribution, the target function in F1. The reason why that's the case is actually quite complicated, is because there's several elements, but one is that when you look at the loss function, in terms of the measure instead of the parameters, it becomes convex. And that's because the parameter enter non-linearly the function representation, but the function representation is linear in the measure, as you can see from the equation which is there. So if the loss is quadratic in F, it's quadratic in mu. This is not enough to guarantee convergence, because you're convex in the wrong, the wrong metric, the wrong topology. In fact, it's not geometrically convex, but that's where there's a bit of work that needs to be done, and you can actually prove convergence. Okay? This mean field limit was first introduced in the series of papers at the right there, left for you, and the global convergence was announced in the paper that we had with Grant, and then proved rigorously by Leneg, Shiza, and back in the paper that is there, and there's been quite a few developments around that. Okay, 2 remarks which are maybe important is that, again, the simplicity here, right, is because we look at the function and not the parameter. If you were to redo the training, you would get different sets of parameters. So the model is not identifiable. Just in the same way as if I were to rerun the movie that I showed you on the previous slides by drawing the initial condition differently, I would get that individually, I would get something which is different, but the flow would be the same. So that statement. But it's important to think about it this way, because it already tells you that it's a way to do, a calculation and analyze them that is quite different from what is done in standard numerical analysis. Now, this is, if you wish, a dynamical version of universal approximation theorem, because it guarantees that not only you have this universal approximation, but in fact it's reachable dynamically by training of the network. This result would not be so interesting if the convergence rate here was very slow. So we need to understand how far is Fm to F as a function of m. But this is where we can use the central limit theorem. And I'm going to go quickly on this slide. It's essentially saying that, well, the discrepancy between the measure, the empirical measure, and the target is a Gaussian measure, and as a result, so is the discrepancy between the neural network representation and the function itself. This is certainly true at initialization, right? Because that's the standard central limit theorem. But there is a dynamical version of this that just propagates that in time if you evolve the parameter. And these equations had been written a long time ago by Brown and Epp and Alan Sisman, etc. Our contribution here was simply to show that in the context of neural network, you can actually analyze these equations, which essentially just look at the way the covariance is evolving, and simply show that in certain cases, it doesn't blow up. So the error remains controlled for all time through training. Okay, so you don't escape the scaling of the central limit theorem as time goes on. And in fact, the result is a little bit stronger than that, because it says that when you train the network, you get an error which is in fact lower than the one that you would have gotten if you were to draw the parameter randomly from the optimal measure, the one that represents the function. That means that even if I give you this function, instead of just drawing parameter from them, you should draw parameter and then train. This would limit, this would make the error go down. And the paper where this is explained are listed here. A few references are there. Okay? Okay, so all of these results can be generalized if you look at the empirical risk minimization. In that case, the only thing that you need to, you need to do is that since the number of data then is finite, right? In general, what you get is that when you do the optimization, you can get in the over-parameterized regime, so if you take the width large enough, you will get zero approximation error. Okay? Now, so the question is simply in that case, what can we say about generalization? And not surprisingly, in view of what I had said before, it tells you that in general, you need to rigorize the loss to control the norm of the function as you train, because we know that that's what control the generalization error. Okay? And so you can do that, and that adds an approximation error term, which is of the order of regularization term that you put in the loss. That's a little bit technical, but maybe the take-home message here is in fact something that links to something else that has appeared in literature recently, which is another one of these surprises, which is that there is no overfitting in the infinite width limit, even if the number of data points is finite, provided that you rigorize. And this is something that was first observed by Belkin, actually, and collaborator, which is that it says that typically, right, the standard picture that we had in statistics is that if you take more and more parameters, think about width, the error would go down. This is the training error. But at the level of the testing error, it would actually start to go up because you would overfit. But it turns out that it's not what's happening, at least not if you overfit enormously. In other words, this is just a part of a first curve, but then there's a second descent that follows. Okay? Explaining this is actually remained a subject of intense research, and a few references are here. I'm just talking about what happens if you go all the way that way in the limit that and there the situation becomes reasonably simple. Okay, and so I mean, if you want to have a little slogan, is that if you control the norm, you don't have generalization error, and the slogan is that you shouldn't worry about the width of your network, but you should control the weights, because that's what is key for the generalization error. Okay, so let me give you a few. What are the take-home message that we have so far? Well, it's summarized in the formula which is there, which is to say that if you train a network with a finite width, sufficiently large, and a finite amount of data but sufficiently large, you should expect that after training, you would have an error bound for the generalization error that should scale like a constant over m, another constant over n to the 1/2. M is the width, n is the number of data points, and then a little bit a term that accounts for the error that the regularization that you need to put to guarantee these results. Okay? Where these constant depends on the norm of the target function. So this is a remarkable result in the sense that this error estimate beats the curse of dimensionality, because you see that the scaling in m and n do not involve powers that involve d. Right? The standard, if you were to do that with classical methods, right, you would have that the 1 over m would be more like 1 over m to the 1 over d, which is dramatically slow. But this is not what you see here. It's 1 over m. Okay? Now, if you think about these results a little bit in retrospect, they are not completely surprising, and in fact, you realize also that they come with a lot of caveats. So why are they not so surprising? Well, it's because there is an instance where we knew that we could beat the curse of dimensionality, at least if we switch viewpoint and we switch methods. And that's the context of integration. If you want to integrate a function on a domain, suppose omega d is a compact domain, I want to integrate f, right? If I want to do that by a grid-based method, trapezoidal rule, whatever, this is plagued by the curse of dimensionality. The error estimates are very bad in terms, it's a curse of dimensionality. But you know that there is a way to get around that, which is to do Monte Carlo. In this specific case, it would just mean draw samples uniformly in the domain and do the empirical average over these samples, because this guy, by the law of large number, converges to this. And the CLT gives you an error estimate. Okay? So now, I mean, so this analogy is kind of interesting because, well, this is only probabilistic error estimate is not a worst case scenario. The worst case scenario is still plagued by the curse of dimensionality, but you don't care because concentration inequality tell you that with very, very high probability things will go right. Okay? However, there is no free lunch, which is that you have the scaling now is like this, but you need to be very careful about the variance of the function. In particular, if the domain here is in high dimension and you simply do what I'm suggesting here, this variance will be very large in general, and so this will also not work, but for a different reason. So you need to control the variance. Okay? But that gives a route into, I mean, there are routes to do that. Okay? And in some sense, what I'm telling you is that what's kind of emerging as a picture is that Monte Carlo that was done, for sampling or integration can actually also be done for function interpolation, and the fact that you have these concentration phenomena that arise is something that, Dave Donohoe coined the blessing of dimensionality as opposed to the curse of dimensionality, okay? But again, I mean, these statements also tell you what are the caveats that we have with the picture that I'm proposing and why this is only the beginning of the story. But first of all, I lied when I wrote that because we can't prove that. The result that we have are asymptotic in N and M. They are central limit theorem type. So we don't know, I cannot prove something like this, or we cannot prove something like that at this level. They are asymptotic in N and M. I would say that this maybe is not that big a deal. But there's other things. This is true at convergence in time, and we don't know what is the convergence rate. It could be very, very slow and itself be plagued by the curse of dimensionality. We know because there are mean field limit that the convergence rate doesn't depend neither on M nor on N. But that doesn't mean that it's simple, and it could still be pretty bad. In fact, there are results that say that, again, worst case scenario that say that typically it could be bad, okay? Whether we can do better, I mean, that's something that needs to be understood. And then on top of that, right, the generalization error is based on very crude bounds. We need to understand, in other words, the data structure don't enter that very much. And clearly, if we want to understand the success of deep learning, we need to do better at that level. And there's a huge area of research. The space that we are talking about, and I didn't discuss that so far, right? The way this space were introduced are these barren space, okay? They are known to be too small, and that's because we are talking about shallow neural network of a certain type. The picture is more general than that, and so you could imagine constructing spaces that are much bigger than the barren space with, the root that's here, but that's not done. And so in particular, the spaces that we are talking about, the one where, where you have these norm gamma that are related to the expectation that I showed at the beginning, what are their property? How large are they? How do they, interplay with other spaces? The more standard spaces of approximation is something that is fairly open, and that's also an interesting area of research. And then maybe the one that is the most open is that unfortunately this picture is true for shallow neural network, can be generalized for deep neural network in certain cases, but not for all architecture, because it is important to keep this interchangeability between the units, which is typically not satisfied in real neural network or deep neural network that are being used. But that there too there is maybe a way to proceed, and this is another active area of research. Okay, let me see. Okay, so how am I doing with time, Giulio? 20 minutes. Okay. Okay. So now, I mean, I tried very briefly to give you an overview of, one way to maybe try to understand the approximation power of neural network, right? And now I'm going to switch gear, and I'm just going to work under, the assumption, the working assumption that we have now a tool that allows us in certain, to represent function that, that have expressivity, power of expressivity that is high enough that they can approximate function in high dimension. And then the question is, well, what can I do with that? If we have that at our disposal, what can I do with that? And of course, there's many things that have been done about that already, but I want to focus on problems that come from scientific computing, okay? And that's what I'm going to discuss in the remaining of the talk. And there's many applications, but there is one that I would like to discuss, which is the solution of PDEs in high dimension. And the reason why I want to discuss this specific topic is because I'm going to discuss problems in which there is a known model but no data, which is a little bit the opposite of what typically you have when you do supervised learning, where you have a lot of data but no model. But when you do scientific computing, you want to solve a PDE, typically you're in the other situation. And I'll try to explain why that's the case, because this leads to challenges, but also some opportunities. I'll try to explain that. Okay, so let's take an example, because it's easier, I think, to discuss example. So I want to look at PDEs that come in variational form. So for example, if you look at the eigenvalue problem at the right there, okay, this eigenvalue problem has a variational formulation, which is the one that is written at the left. I wrote it, there are constraints that you need to put, but for simplicity, we can leave it at that level. Okay? And so, the fact that this variational formulation exists is, of course, at the core of standard numerical method. Like when you do finite element, what you do is that you're actually discretizing these integrals, right? And then you have weights that enter them, the discretization quadratically, and then you make an optimization, and that's the way you proceed, right? But again, this is plagued by curse of dimensionality, and that's why scientific computing with PDEs has been a low-dimensional affair so far. But when you look at this problem, you realize that, in fact, it is tailored for a deep neural network approach. Okay? And in fact, that's something that has been termed the deep Ritz method by Vanden-Eijnden and Jensen. And in fact, it's quite similar, but using neural network or something that existed a long time before, which is variational Monte Carlo method. So let's explain what it is. Well, it's simply saying, instead of using some finite element representation, let's just use a neural network to represent the function. I have written it compactly like that. Theta here means all the parameters in the network that needs to be trained, and it could be a deep neural network if we want. And then, well, if that's the case, you can actually think about the loss over there, the objective over there, sorry, as a loss for the parameters. Of course, you cannot evaluate this loss, but you can sample it. Because in the case that you see there, that's why I chose this example, you see that the denominator and numerator are both expectation with respect to a Gibbs distribution associated with a potential U. So if I draw samples from this distribution, I have an empirical representation of the loss, which is the one that is there. If I have an empirical loss, I'm in business, because now I can optimize my parameters just by doing gradient descent, or stochastic gradient descent if I do many batches that I generate over there. Okay? And many people have been looking into problems that are of this type or similar type or broader. And I just I've listed a few names there. That is a very partial list at this point of people that that have worked into this area. Now you notice that there is something which is different, which is what I told you at the beginning, which is that, right? You need. I wrote the loss slightly differently for simplicity, but you need to sample the loss, right? You don't have any data that is given to you beforehand. So the sampling you need in the problem. There are no xi that are given to you. You need to generate them, okay? And that problem is difficult per se. Because it's hard to use, because typically we are interested in solving this eigenvalue problem in situations where there is metastability, and I'll give you an example later, but in a nutshell that means where there is a low-lying eigenvalue in the problem, which is corresponding to very slow time scale in the system. What are these very slow time scales? Well, these very slow time scales are the ones that are responsible for metastability, which means that sampling this measure is very, very slow with standard method, okay? But there's something which is even more important and goes back to this issue of data structure, which is that even if I were to give you a data set from this measure, it would not be in general a good one, because it turns out that the objective there, and that's the rule rather than the exception, is dominated by rare event itself, which means that if you try to the estimator they've written there is actually a bad estimator, even if you manage to generate the data from your Gibbs distribution, okay? And you can actually quantify this. This is the realm of online learning. You can quantify that the variance of the empirical loss directly affects the generalization error. we showed that here, and it's building on previous work by Blay and co-worker. Okay, so let me try to explain that because I think that's key. It gives us. So this scientific computing problem, where there's a ground truth, give us some window into trying to understand what's the origin of the problem with the generalization error. Okay, and so here's a little example. It's a 1D, so it's not very interesting, except for that it allows for visualization. If I want to solve the PDE there, with Dirichlet boundary condition, right, in a double well potential, the solution is this sigmoid shape. Is the one that is in blue that you don't see somewhere over there. Okay? And so you can see that it's very easy to parameterize this just by using a sigmoid. So let's take a neural network representation. This, again, is a cartoon, where only two parameters, which is it's a sigmoid, and I just need to tell where is the sigmoid centered and how sharp is it, or steep. Okay? And now, here's the problem that you see, is that if I generate quite a lot of samples from the Gibbs distribution associated with this at low temperature, I will have a lot of samples near the minima of the potential, which are there and there. I'm looking here at the PDF. But I will have very few samples at the barrier. Unfortunately, the sample at the barrier, which is the saddle points, if you will, are the one that dominates the error that you need actually to get a good approximation. And you can see that because in this example, unlike other more complicated examples, you can actually plot the population loss. Here it is. And then you can plot the empirical loss, and you realize that they are completely different. And why are they completely different? Is because you're lacking data at precisely the region where you need them, which is the transition region. Okay? And correspondingly, unfortunately, the code doesn't show very well. If you do the optimization of the population loss should be done, you would get an excellent approximation of the truth. These are the blue and the red curve that superpose there on the first, the one on the top left. But if you optimize the empirical loss, is the yellow curve that unfortunately maybe you don't see very well, but actually it's a bad approximation. It's too steep and it's not at the right place. And that's simply because it's cutting somewhere there where there is no data. Okay? So one needs to do better than that if you want to do something about this problem. And there is one way to do it. So this is, it's a curse and a blessing in a way, which is that now we can say, well, we can do online learning and we can render it active. Okay? And how will we do that? Well, we'll make it active in such a way that we'll combine it with important sampling so that we get the data when we need it, right? This really should be termed reinforcement learning, but reinforcement learning, the terminology that we take, and is something a little bit different, so we don't use it, and we used active online learning. But okay, so what's the idea? Is that we will try to do some important sampling where we're going to use the information that we have, the current information that we have about the function through the neural network, to tailor the data generation to it, and then have a feedback of that type. Okay? And we're going to borrow from the standard toolbox from computational physics, which is that the two of them will feed in one another. Okay, let me show you an example that illustrates that, right? So I'm going to take a high-dimensional example now, which is essentially it's a set of continuous spins, and I've written so they live on a square. The squares are shown there, right? And these continuous spins have two forms of interaction. One, which is the interaction energy. The nabla there is the discretized nabla, right? That means that all the spins want to align, and then there is another. So it's a simple model from that viewpoint. And it's not a random potential or random interaction, right? This is the simplest one. And then there is an interaction term there which says that they all want to be aligned with either +1 or -1. And then you can frustrate this system simply by imposing Dirichlet boundary conditions. So you freeze the spin to be up on the sides and to be down on the bottom and the top. And then you can look at what are the minimizer of this energy. And there are two minimizers. I'm showing you actually not the minimizer. I'm showing things at finite temperature. But the minimizer are actually very simple. All the spin align in the core, and they just align with respect to either these boundaries or these boundaries. These are the two states that are there. Okay? Now, if you consider the system at finite temperature, right, then what happens is that, well, the Gibbs distribution is very highly peaked at these two states. But transition between them are possible, right? And we would like to understand how they occur, okay? And so what does that mean? That means we want to look at the Langevin equation that's associated with this system. Right? This Langevin equation has the Gibbs distribution over the spins as equilibrium distribution. And to understand the metastability, we want to compute what's called this committer, which is essentially, it's a way to approximate the leading eigenvalue and eigenfunction in the problem. And that's solving, it's a PDE in very high dimension because the PDE where each of the spin is a variable, right? In this case, there's 144 dimension. And the way we're going to solve the PDE is simply by optimizing this guy viewed as an objective function. Okay? We were not the first doing that, but we are the first that are really doing it with important sampling, and I'll show you that it's important. Recently, there are other, there's another work quite interesting that appeared where it's done with tensor network instead of deep neural network. We simply use deep neural network. Okay, so I'm not going to give you much of the detail of what was done, right, except maybe to describe this. Actually, this is quite detailed. So what we're going to do is that, so we need to do the optimization, we need to sample this loss. And as I told you, this is complicated to begin with because we cannot sample this distribution very well. It's metastable. And on top of that, we need to have samples that are very unlikely on that distribution because we need to know what's happening at the transition state. Okay? And so the way we did it is like this, is that we use the level sets of the function itself to do umbrella sampling. What is umbrella sampling? Is just you do sampling, but you restrict the sampling not in the full space, but in a band that is around a region that you prescribe, in the umbrella. Okay? Umbrella sampling is really a method that is very widely used to do important sampling, but it comes with a caveat which says you need to define what are these umbrella a priori, and that's quite hard. Here we say, well, there is a way to define them. Let's just use the level sets of the function that we are trying to learn. Okay? And then umbrella sampling enough doesn't work. You need to combine it with replica exchange, another method where you actually use replica on each of these level sets and they interchange. But that's a way to do the important sampling. And we do that to get the data. The data allows us to optimize the function itself that change the umbrellas, right? And then we proceed. This is a little cartoon in 2D where it shows you what happened at convergence. So this is a 2D potential. That's the equivalent of the U of rho, if you wish, but only in 2D. And these are the level sets of the function Q that you are trying to learn. This was done with a neural network. And the way the sampling is done, if you wish, is that sampling is done by doing sampling that are restricted in neighbors of these windows and recombined in such a way that you have sample where they matter, which is actually here. Okay? And so, and the pseudocode is written there, but that's not very important. And then, if you do that, the surprising thing is that it actually works. In other words, you can train the model. So you can build a network, right, that starts simply with a step function that interpolates between, in this 144 dimension, between the state at the left and the state at the right. And then you start the procedure, and it converges in the sense that it tells you that the loss is decreasing. And if you redo it for many times, you see that the loss is decreasing consistently. So, in a way that it seems to be not tailored to, this is already an indication that it should be a good generalization error. And then in this example, you can do something which is, you can analyze the result actually. Because I can show you what are the samples on each of the umbrella. So let me go back to this so that we see. If you were to look at these guys here, each of these windows, and you had to ask where is the Gibbs distribution on these windows centered, it would be here, 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 etc. It would define a path that goes from there to there, right? Because this is an unlikely place, this window, but on that window, this is the most likely state, if you wish. So we can actually analyze the result because, of course, in the 144 dimension, I cannot show you these windows, but I can show you the samples on the windows. These are the samples on the windows. And you see that they are showing you a path which a posteriori is a very natural one. That's the one where you see, well, how does the transition occur? Well, it just goes by moving the domain wall, reconnecting in the center, and then evaporating, putting them on the other side. And the equivalent of the saddle point is this hourglass shape that's there. Okay? So the model is trainable. And in fact, we know that this is the result because in this case, and that's why we picked the example, we can compute this path by other means. In particular, it's a minimum energy path that can be computed with string method, which is a method that we developed before. This is the continuous version of this problem. And what I'm showing you is a movie that shows you the heteroclinic orbit of the minimum energy path that go from a minimum to the other minimum by passing by a saddle point. The saddle point is the cross. So we knew, but the neural network is rediscovering this without a priori knowledge and without any data at the beginning, which is the remarkable fact. Okay, so I mean, I'm slowly getting to the end of my talk. There are many other applications that you can do, based on these things, which is again problem where there is no data, right? Where there is model but no data. A few of them that that we have done, and the resolution is not very good, but we have looked into how can you, in fact, whether a problem where generating the data is the problem is when you do Monte Carlo, Markov chain Monte Carlo sampling to sample, high dimensional distribution. There is a way to do that by augmenting them with normalizing flows, which in fact allow you to generate samples to do non-local move. And again, you can do something where there's a feedback loop where you are using the current data to train the normalizing flows, and then the normalizing flows allow you to generate more and more data. Okay, these I work with also with Grant and with Marie-Lou Gabriel. We have been looking into training energy-based model. When you train an energy-based model, right, you at some point you need to do a sampling on the trained energy, the one that you trained, right? So these energy-based models are used to represent data. They are generative models that are fairly popular. There is a sampling problem there that needs to be tackled, and again, this is a place where there can be an interplay between scientific computing and sampling of the same type, in fact, of the one above. And then we are moving on now into using neural network to solve time-dependent PDEs and other problems using, again, the approximation power that these neural networks have. Okay? So, very quick conclusion. I have tried to show you two things. First, that there are a set of theoretical results, among many others, that support the empirical evidence that indeed deep neural network can outperform standard interpolation method, at least in certain cases, and we understand better when and why that's possible. Remember, the curse of dimension is there to stay, but this tells you that there are cases where you can bypass it in a way. This offers very exciting possibility for scientific computing, okay? But of course, I mean, it's completely clear that there's a lot of work to be done because the network architecture, the way you do the training, the way you do the data collection, et cetera, needs to be understood on a case-by-case basis. And at this point, we have very little, know-how on how to do that, right? And but that's exciting times because there's a lot to be done in this area. Okay. And now, I mean, and as a final slide, I want to let you read maybe a little text by Lewis Carroll, because this is what we're observing here is a revolution potentially in scientific computing, but it's a revolution which leads to interesting questions, which is we can solve PD in high dimension. Okay, but why would we want to do that, and in which case do we want to do that? Because at the end of the day, it will give you a complicated solution that maybe you don't understand. There's many complicated functions that we know and we don't know. We can evaluate them, but we don't know what they mean. Okay, and so there's a question of which problem are actually treatable and which one are the one that we want to treat and why. And this is kind of changing a little bit the vision we're going to do scientific computing. And this little text by Lewis Carroll kind of encompass that in a way because they are discussing the case of the people doing the maps, and then they scaled the map up all the way to the point where they became the size of the territory itself, because that was the most detailed, and then they realized that that was useless because okay, so that's the text. So I leave you that as an open kind of food for thought, if you wish. Thank you very much.
Time for questions. So, okay.
Thank you very much. So until 1 minute to the end of the talk, I had the impression that you are kind of taking away everything that from the old days and you replace everything. Right now we have no models anymore and everything changes. The only thing that seemed stable was gradient descent and stochastic gradient descent. And then just in the last minute you said there are maybe normalizing flows is that a way to replace even the gradient descent? Or is that going to stay? Are we going in 50 years, are we still going to use gradient descent and solving equations like that? That's just
Okay, so it's a complicated question. It's an interesting one, but it's a complicated question. So on the side of gradient descent, it's clear, I think, that there's a lot of work to be done to try to understand whether we can do better than it, and how fast does it converge and all that. Like the standard tool like Adam that are being used are not they're very efficient, but they are not very well understood, I would say. But your question also alluded to a point which I think so I don't know what you want to say, but I want to reemphasize. I mean, in my mind, these tools of machine learning, right, are not black box that will solve all of our problem, which is that we can know, you're a student, forget about studying math, physics, or anything, just go into trying to find how TensorFlow is working, or JAX. No, I mean, clearly, I think that it's exactly the opposite. I think it's a very fertile ground for discoveries, but clearly it has to be understood theoretically, and for that we need all the apparatus that from physics, math, computer science. What's interesting is there's going to be a feedback, right? It's not that we're going to come with the tools that will allow us to solve this problem. It's going to be a feedback that will grow all the fields. But clearly, I'm not advocating of burning all the the math books.
Here. Yeah, I had a question about the interacting particles. Mm-hmm. So you have this recursive force, and intuitively, as far as I understand, this force is to make sure that your units are not redundant with each other. So because if you have two units in the same place, they do the same thing. So is that why they have a recursion?
So I put this movie.
Right. So I know the movie
because
is a cartoon,
I like it visually, but right. I realize that it could be misleading. Okay, in the sense that the analogy here is really this: when you have a neural network with a certain architecture, right? The loss is given to you. That's what it is. Okay. When I did my cartoon, I tried to pick an F and a K that would be visually pleasing, but they have nothing to do with what's happening in real network.
So you mean they don't actually? There's no repulsive force between them?
Well, they need to be, because we know the K plays the role of a repulsive force, yes. But interpreting it as a Ritz potential is maybe a little bit too much. But it's clear that there is what you say, which is that somehow the units are distributing the task in such a way that they do the best they can. No, it could be that they could all collapse into one if that was the best. Right? We don't know. In fact, I'm not saying, just to avoid confusion, this part of the talk, right, is really just trying to give a framework to analyze what's going on, but there is nothing that is being changed. This is, it's a bit different what you do in practice, because you would use a discretized version in time of this, and you would use mini-batch and things like that. But at the end of the day, is to try to understand why is it that if I run these dynamics, I actually get a consistent answer in terms of the function representation. So that's what this explains. And then it branches out into saying, well, once I understand that, maybe I can try to accelerate things. For example, we have done work where the neural units, you can add a birth-death process onto them, which is that they come with a fitness. Some of them disappear, the one are duplicated, etc., etc. But it's just.
I understand. I think my question was that can you use this analogy to understand how also gradient descent works, in the sense that if you have these repulsive interactions, maybe you can get the system stuck. I know it's a cartoon, but the movie you showed eventually was a crystal, actually, not a liquid, because your guy is aligned. So I was wondering whether you actually expect to see this kind of dynamics in real learning of this kind of frustration.
Yes, whatever is the generalization that in higher dimension. But I think all of these analogies are always dangerous. But I think there is a few things here that that you can learn just by features that are there, right? Like individually they do certain things that are different. In this case, what you're creating actually is a crystal, but with defects and and fault lines, because because there's a mismatch between, well, first of all, because it's created randomly, and because there's a mismatch between the geometry and the crystal itself. So all of these features probably have analogies in the training of neural network, in particular in the fact, that the global picture is always the same. That's kind of the law of large number. But if you look at the fine detail, they are different, and that's the error that you are making, etc., etc. But I don't want to push this analogy too far. But it is, if nothing else, it is something where people that come from physics and have seen these things, there is a certain intuition there that probably can be transferred at least in part into what neural networks are doing, at least the shallow one that I've been discussing in this part of the talk.
Yeah, so just a follow-up question. So in the mean field limit, the evolution equation for one parameter, theta I, or one set of parameter, theta I,
Yes.
depends on theta I, and then it depends in a mean field way on the rest of the system, right? So it's the sum over j, k.
Yeah,
k.
so you see.
So my question is, this is in the mean field limit. Can you think the way to test it? I mean, whether real network, how much are close or far from the mean field limit? Because if m is small, you will have fluctuation, and it's no more true that it just depends on all the other ones.
So this is, you're going into the, so the scaling that you get for the mean field there, right, which the mean field comes into here, right, at the end of the day. You see that this is unit theta, unit I sees the average of unit j because this is an empirical average, right? Now, if you ask yourself, why is that coming this way? Well, it's coming this way because in the way we did the analysis, I put by n the 1 over m there, right? Now, what does that, if you want to understand this in a more kind of practical way, right, this 1 over m is in fact a scaling that you put on the c, the external weight in some sense. And you could decide to change that scaling and see what happened. And in particular, there's been a lot of work by Arthur Jacob, etc., that introduced what's called the neural tangent kernel, NTK, right? Which is also called by Francis Bach and Yannick Chiza lazy training, where they look at another scaling, which is you would replace the 1 over m by 1 over square root of m. And in that case, the picture is different. In fact, in that case, it's not that different in a way, because at the end you end up having that to recover the means field limit, but in a linearized network. So it's much easier to analyze. You can understand convergence much better. In fact, it's a regime in which neural network or deep neural network reduces to random kernel method. Okay, so certainly that's part of the story. In that in that scaling, we know that there's a scaling in which this will happen, but we also know that there are features that NTK would predict that are in contradiction what was observed when we train real neural network, because one of the features of the NTK is that all the units only moved a little bit, right? And so there's very little adaptivity, okay? Whereas in this scaling, there is adaptivity. All the features are actually moving and adapting, and we know that in certain cases, this seems to be consistent with what the network are actually doing.
Yeah. For sure, I think in realistic case, the parameter moves more than in the NTK case. But what I was wondering is, even if they move of order 1, this mean field, let's say, interaction is special, and one can wonder how much, again, realistic networks are, let's say, mean field, or I think it would be.
This is related to the question which I say is not very important, but in fact, it is, which is that when we look into this, we look at asymptotic regimes, right? And then at the end of the day, you need to figure out, in the parameter, you have many parameters here that you can send to infinity that are big, and where are you, and whether there are phase transitions between them, and how do they interplay. And that's also very interesting. Yes. I didn't have time I have slides on the NTK, but it would have been too much, I think.
Okay. Thank you very much, Eric, for your very interesting talk. So I have a question, or I would like to hear your comments on the following problem. So there are a class of problems called inverse problems, where you have some model with some parameters you want to estimate. Yeah. And then maybe you can simulate the data using this model, maybe PDE or something, wave equation, whatever. And then, on the other hand, you have real observed data.
Yes.
And then you want to estimate those parameters in the model. And then typically what people do is you need to start with some good initial estimate of the model parameters and then run the simulation. Then compare the simulated data with observed data. And then you tune the parameter again so that the data matches, simulated data matches with the observed data. But then again, this objective function, okay, maybe have a lot of local minimum, and then all sorts of important constraints about model parameters and a priori information about those models and so forth becomes very important. And under that kind of context, in your viewpoint, how a neural network help in this kind of situation?
I mean, the neural network are obviously used quite a lot these days to do, inverse problem of the type that you are discussing. I am not an expert in that area, so I don't know if I hear from many people that sometimes they are, they do very quickly and very easily things that other methods were doing just as well. So I don't want to comment, too much on that. Simply, with respect to the kind of scientific computing problem I was looking at, they are somewhat different because the one that you are describing are again problems in which you have data, right? And I was, I focus. So it's, so all what we learn about the trainability and the accuracy of neural network in general would probably apply to these, at least give some hints onto what can be done in the context that you are discussing. As I said, the specific problem from scientific computing that I focused on are more problem where you don't have the data to begin with. There is no, right, like for example, in the case of a committer function, it's actually fairly difficult to have estimates of the committer that you would feed. It's not impossible, by the way, but it's difficult. And so, I took another route. These problems are very interesting, but I really am not an expert in them.
Thank you.
All right. Okay, so, last question.
So the first part of your talk was about essentially one hidden layer network, and then you can see clearly that the nodes on the network are all interchangeable. Therefore, it makes a lot of sense to treat them as particles. Can you give a hint of how people are thinking about 2-layer, 3-layer, or multi-layer? This density, the fact that actually the beautiful result here depends on the density, not so much on the individual nodes themselves. That is and are there hints of things like that happening in bigger networks? And
so there's, I mean, for general architecture, it's difficult to apply this. At least we don't know to do it.
But maybe just like fully connected.
But they are so one set is like if you use ResNets, for example, like the one that like if you know a little bit about neural ODEs, these type of thing, where essentially you think about a shallow neural network that would be the input of another shallow neural network, and then again and again and again, right? So in other words, you would feed this FM, right, to another shallow neural network where you would have the same structure, but you replace the X by FM, and then you do it again and again and again. That one is perhaps the simplest case where you can generalize that picture, where what you would have is that there is a mean field limit in every one of the layer. Okay? So the problem is that in that setup, for example, you right away see that it becomes quickly more complicated because in particular, in this setup, because there's only one layer, if the loss is quadratic in F, right, it will be quadratic in the measure. Or if it's convex more generally, it will be convex. But if you have this compositional structure, then you are actually already losing that. So it's not, so the mean field picture is still there. You can still define, at the level of defining these spaces and the error that you make, it's still a way to do it. But the analysis of the convergence properties by training become a little bit more complicated. Okay? Now there are other architecture that you can, where you can imagine that you have units that are individually very deep, and then you combine them into making a large layer, and then you connect them through constraints, at the bottoms, like at different layers. That also is amenable to this type of analysis, which is maybe more general than the rest nets. Okay, and there maybe you don't lose so much of the, the convexity property, etc. So this viewpoint is certainly not applicable, universally, right? That's clear, but it is more general than just looking at shallow neural network.
All right, so, well, let's thank Eric again.
Thank you.